Hello, my name is Tarik Hamedović from Chili Chips, and I am today going to present the Wireguard FPGA project. So, what is the Wireguard FPGA project? It is a modern Wireguard is a modern secure data tunneling and encryption method that is coming to the forefront. There exist software and hardware implementations of WireGuard, but the software implementation is pretty slow, while the hardware implementation is expensive and based on proprietary closed source IP blocks and tools. So the goal of this project is to bridge these gaps with an FPGA open source implementation that is written in System Verilog HDL. So for this, we use an inexpensive platform with 4 Ethernet ports. The platform uses a Arctic 7 FPGA and is developed by A-Links. All the gateware is written in System Verilog and Verilog. Here on the next slide you can see the FPGA boards that we are using for this project. And the tasks generally at the beginning were to write some basic examples on the board to bring it up, so to say, then to implement the basic statically pre-configured WireGuard link, to develop and integrate embedded management software, the control plane, to make the VPN tunnel, and then to test and profile and port everything to the open source OpenXC7 platform.
Then the in-depth review of the WireGuard ecosystem and the design blueprint. So the take 1 we have already done. Then the take 2 is the implementation of a basic statically pre-configured WireGuard link. We are currently doing that. It's mostly done. Then we integrate it in the embedded management software. So we make a control plane to take the WireGuard link. Then make a VPN tunnel and testing, profiling, porting, and so on. And okay. So this is the design blueprint that we have. So it's a 2-layer architecture. So we see two layers that are, one is the control plane that manages IP routing processes and executes the WireGuard protocol, and the other is the data plane that performs the IP routing and cryptography. So the lower one is the data plane, and the green one, and the red one is the control plane. So the control plane will be implemented in software as a soft CPU, while the data plane will be fully realized in RTL. And okay, this is overall the hardware block diagram. As I said, it's pretty complex. So, and here as well, the red one is the control plane, green one is the data plane, and the blue one, I forgot what the blue one is. Okay, so everything we can see here is the speed of the clock that does it. So the blue path is the 125. I think that's the physical one. Yeah. So the blue one physical, that's the 125 megahertz. The red one 80 megahertz and 256 gigabits per second, and the 80 megahertz around 10 gigabits per second. So later I'll go exactly into the implementation here that is done. So in the hardware theory of operation, here we can see generally what everything on this slide is. So we have the physical controller, the 1G MAC RX FIFOs that are on the left side, and the transceive FIFOs that are on the right side, the header parser which extracts the data that is important on the input and the output side, and the packet disassembler and assembler. So the one when we get the input, one disassembles it, and this one assembles the UDP packet. The decryptors, which we use SHA-SHA-20 and Poly 1305 algorithm, then the IP lookup engine, and overall, so this one is okay. Then the software class diagram, so that's the red one. These are all of the functions that are done in the Wireguard agent that we can see in the top right corner. These are all of the things that the soft CPU would need to do. And this is all listed here. I mean, and it's pretty complex. I don't know everything about this. It's really theoretical. So, and most of them are algorithms that are developed that we use, that we develop ourselves or use. Okay. So these are the three domains that I explained, and here there's something interesting here to say that with the CSR that we see here. So from the there's a layer between the data layer and the software layer above. So the red and green lines, that is called CSR or HAL, and here we needed to implement our own, because Wireguard's control plane must update the crypto key writing table atomically, and when we want to update it and the data is already being processed, we cannot pause it. So we used something called atomic CSR update that you can see here. So it comprises of multiple stages. So when the CPU needs to update, it sets the P flag, and then the active P signal instructs the input multiplexer to transition into the pause state after completing the current queue. So we bypass the problem that I said before, and the CPU periodically checks whether the bits are ready. Once the first component finishes processing, it clears the data path and deactivates the T-valid signal. Then the CPU continues to check if the ready bits are in the FCR register. The processing of remaining packets on data path clearing continues until all components transition to idle state, that we can see is happening on the GIF. So then the CPU updates the necessary registers over multiple cycles. So the control flow generally, so this is the complex part. I don't know if I'll go too much into detail here. So to illustrate the operation that we are going to do with this project, so this is the simple part. I mean, the simple, we have a host A and a host B and two Wireguard FPGAs, and we want to send data to it. So what do we need to do? We need to send a handshake initiation from peer A to receive the handshake initiation on peer B and send a response back to peer A. Then the peer A receives the handshake response, and we need to do encryption and tunneling on the ICMP echo request packet from host A to host B, and then detunneling that and decrypting that from host A to host B via peer B. So generally, there are, I think, 56 steps here that are so I mean, they repeat, so it's not going to be that complex, but I don't know if you can see overall, there are numbers. So the Wireguard agent, there's a 1 there. And then in the CSR HAL, there's a 2 here. So that's how the data flows. So we have 1, 2, 3, 4, 5, 6, and so on, 7. So the data goes like 1, 2, 3, 4, and then 5, 6. So it's like this. I mean, it's all marked. It's a pretty nice picture overall. But so the peer A establishes the VPN tunnel. The CPU transfers the handshake initiation packet from the RAM through the FIFO on the left via the CSR, that is the layer in between. Once the entire packet is stored, the round-robin multiplexer services the packet from the FIFO and ejects it into the data plane pipeline. Then in the first 3 cycles, the header parser extracts the important information from the packet header, such as the destination IP address and type of WireGuard message, and supplements the extracted metadata to the packet before passing it along. So here in this part, it's important to know that we bypass the disassembler and decryptor. That's going to be used only in the later parts. So then we, based on the header parser, we take the demultiplexer and transfer it via the transmit FIFO. That goes in the 8th step down there, writes the MAC address as the source address, calculates the FCS and adds it to the Ethernet frame and sends it to peer B. And now the data goes from here back. So it goes from the port B that has received that. So here's the 9th step, and then goes back through the RX. So because we again receive the data on the other FPGA, and goes through the same thing back to the WireGuard agent. So in the next step, that the WireGuard agent has both the initiations, handshakes, and it sends the handshake response. So next step, we are again back at the WireGuard agent from the port A, and it goes through the steps again, so the HAL, FIFO, and again to the, so you can see here, it says site A, handshake response. And then later on, we are at site A that transfers the data. So again, we see we are, what step? It's here, so just a second, so it's 4. We take 26, we go to 33, 34, okay. And then we look at 35, it's here. Okay, we are here. It takes that one and it transfers the data. And now site B also transfers the data, but in this part we use the decryptors. You can see when we are at site A, it goes from here back again through the FIFO, through the header parser, but now we use the encryptors. And here, when we use the site B, we use the decryptors that we got the data A from. And again, that's the, I tried to simple it down, it's pretty complex, but this is just to do the simplest data line, just to send hello from one end to the other.
Okay, so the software part is active just during the initialization of the tunnel, and then the FPGA.
Yes.
Part, then it's not needed. Okay.
Yes. So the red part is the agent, the I don't know, the curve 251. This is everything here. So it's those are just algorithm implementation for encryptions, hash functions for MAC authentication. That's everything in the software part, and everything in the green is in RTL. So, and we have an interesting thing as well. It's a simulation test bench that one person is helping us. He's called Simon Southwell. He has something called a virtual processor which he made. It's called vProc, which helps us in simulating everything. You can see using his vProc we can just plug a literal virtual processor. He has its own SoC CPU, but we can use other ones like the Pico RV32. The Edu Boss 5 is something that Chili Chips has made. The person that Tarik that did the stress testing worked on the Edu Boss 5 as his bachelor thesis. So the vProc here, we use everything in that for our simulation, and it's a pretty powerful tool, mostly written in C, I think, or C++. It can run a natively compiled test code. It can run the application natively within the auto-generated HAL, and can run RISC-V compiled code using the RV32 RISC-V ISS model. So overall, that's the Wireguard project. Here's a QR code link for the GitHub. Overall, you can just type in Wireguard/FPGA. It's the first thing that pops up. So I hope I grasped your attention a bit. So for this project. Okay. If there are any questions, maybe I don't know if I can answer them because it's a pretty complex thing, but I'll try overall.
What have you implemented from all this complexity stuff? Some modules in the middle or something?
The thing we have implemented, to my knowledge, the latest thing that we are doing is that we have implemented are these cha-cha encryptors and decryptors. We have the FIFOs, I think, and the next part that we are trying to do is the CPU overall. We are trying to make that one work and integrate it. We had some trouble with it.
What is the size of the data of these cha-chas? Do you have one full VRAM of some, I don't know, UDP packet, and it is entirely encrypted or somehow partially, sequentially? How does it?
I will, if Yasmin is in the call and he can help, that would be great. But overall, I don't have the answer to that question. Yeah.
Very briefly, the process for hardening the cha-cha encryptor and decryptor is a multi-step thing. So we start from C code, which is in the Linux ecosystem that the original author of Wireguard has wrote. Now we decouple it from Linux. That's the first step. Turn it into bare-bone C, bare metal C that doesn't depend on any Linux calls or functions. And now that bare metal C is going to run on RISC-V soft CPU in the red, in the pink area up there. That's what we use to kind of test it out, and we also need the encryption function on the control plane. So the next step would be to now take that C and push it through high-level synthesis, HLS, using the pipeline C tool. So this basically sanitized encryptor that's been validated on the bare metal RISC-V is now going to be hardened into FPGA gates using high-level synthesis methodology. So in that way, we try also to test out the pipeline C tool, which is an open source HLS tool, relatively modern, recent, has its own problems as well. So we want to give them a favor and also learn along the way. So that's basically in very short what we plan to do with the encryption decryption engine.
Okay.
Is that
easy, huh?
Yeah.
Now it's being polite, but when we are having internal conversations about high-level synthesis tools, well, so far we have found those as jokes, but well, maybe. Okay. Good luck. Yeah.
which one have you used? Which ones have you used? Have you used the Xilinx tools or open source tools, or which ones have you had the trouble with?
I never use it. I hope I'll retire before before I'll be forced to use any high-level synthesis tools. Well, I'd rather stick to what's more palpable, because with high-level synthesis tools, you are actually giving away the complete freedom to the tool to do whatever the tool thinks to do. But how to map this on the pipeline? So, do you have any info on the pipeline itself? How it's structured? How do the packets flow through the pipeline? Are they pushed a whole packet at a time or in smaller slices? Is there any comparison with, are you maybe reusing anything from the Net FPGA project or something like this? Because Net FPGA has a similar pipeline structure, at least from the high level perspective.
I don't think we use.
Well, no, just a sec. So bear in mind, we are using high-level synthesis as a point tool for one particular function in the overall data plane. And that particular function is very math intensive. It's basically encryption, decryption. It has a lot of shifting, bit shifting, barrel shifting, and multipliers in there. It's very data path focused centric function. For the rest of it, the top level is basically just regular RTL, HDL, system analog. And we did use for the front end, just from the entire Ethernet processing, MAC and stuff, is basically borrowed from another open source project, not Net FPGA, but Corandom. There is a well-known open source project that, amongst other things, provides Ethernet libraries. They provide PCI Express libraries as well. We tapped into their Ethernet portfolio, and we pretty much reused it as is with small adaptations. For this front end that's shown on the bottom, Ethernet front end that's shown on the bottom part of the diagram. So what is really the genuine new thing on this project is the middle part, the data path engine, because we are borrowing, RISC-V soft code from someone else, kind of adapting it. We're borrowing the bottom part from Corandom library, and we design on our own this middle part, data path engine. We go through the HLS, that's a really new novel thing, and then the integration is also a big part. Putting it all together, making sure those 56 steps work as one integral entity. That's really the essence of the project. Integration of the different hardware components as well as hardware-software integration, and then pulling in the specifics of the data plane engine.
Okay.
Any other questions?
Yes, who is managing the packet fragmentation, or the packet is defined from one side? For example, you have a long IP package that is you have to decipher. You have first, you need to collect the whole packet and then decipher it. Who is dealing with that in this block? Or how are you dealing with this?
Well,
there is.
You can answer, Yasmin.
Yeah, there is a hardware lookup. The first block is a lookup engine.
Yes.
There is a hardware lookup. There is a parser that's done in hardware, IP parser, MAC address. So there is a part of RTL code that hooks into the header, extracts the information that's needed, and based on that information decides how to process it, which of the blocks to turn on or turn off, basically which ones to bypass, and where to send the packet to. So what is shown here, in white, the white blocks in this particular on this particular diagram are basically bypassed. They are not in use. They are not engaged in the communication, and that's the result of the control plane deciding based on the information in the header which blocks need to participate in the particular step.
Okay, but the IP lookup is for transmitting. I am wrong?
So it goes on both sides, I think. So here.
Okay, so it's something that is.
Yes.
Okay.
It goes when the data goes there and there. So it's.
I mean, there is a lot of things that are not shown here. There is the sideband channel also that flows with data. There is probably 10 bits of extra information that goes along with the 128 bits of data. And those 10 bits, along with the information that comes from the control plane, decide what's going to happen in the subsequent block. They configure it accordingly. Okay, in this picture you see basically 4 blocks in action, and 2 are bypassed in the middle section. Again, depends on the needs of the stack. Whether we are encrypting, decrypting, or doing something else.
That's it. More questions or Miguel is thinking. So
No, I was trying to see because you are the disassembling the UDP in the stage 50 after
Yeah, 50 is
50.
Yeah.
So the UDP there you have to unfragment the IP package and UDP package because there are 2 different things. It's okay. That is what I was thinking. I don't know. Is maybe sometimes somebody said, okay, this is the fix. I fixed the packet in, I don't know, the MTU, so it cannot be fragmented. You can send the system that the UDP packet is not be fragmented. But it was a question of curiosity. I don't know if maybe you are doing that or not. At least I implemented for Scopio a small UDP package. Force the system not broken the package, because if not I have to do that. And if I lose one of the packets, and it's a lot of work in hardware. So this is why I was asking that.
okay, yeah, we can end this talk and thank you, Tarik. Thank you, Yasmin.